Welcome. I want to say a little bit more about these fusion rules in topology. So here are a few definitions. What we do is we extend cohomology from closed sets, from simplicial complexes to open sets. So if you look at the simplicial complex, then itself is an open set in itself. But so this is a generalization, and the cohomology still works, but there are a little bit surprises. For example, this is an example of an open set, but it's far from a simplicial complex. So it consists of 4 different stars, union of 4 different stars. And there is, for example, no set of cardinality 3, which means that the Hodge block, one of the Hodge blocks, is a 0 times 0 matrix. So that gives us also a Betti number 0. And so we can do everything algebraically. It's linear algebra for every open set. We have we can look at matrices, we can look at the kernels, and so we have these Betti vectors. And what I realized a couple of weeks ago is that it actually behaves quite nicely, usually with respect to addition. So these are these joint sets, right? This is a closed, for example, this is a closed ball, this is an open ball. You put them together, you get the 3 sphere, and we get the addition of the Betti numbers. So in some sense, the open set captures the volume form, and the closed set captures just the 0-dimensional part. So I just want to keep this short and look at a few examples. This is maybe the simplest example, right? We have an open set, an open interval, and so in this case there are no points, no 0-dimensional points. So there is only this interval, and then we have just one times 1 block and a 0 times 0 block. So the Betti vector is 0, 1, and that matches. Of course, the other characteristic is -1, because we have just one odd-dimensional part of space, and the 0-dimensional parts are empty. Also, this is a star. For example, in the Whitney complex of the complete graph, we have just a star, and here the Betti vector is 0, 0. That's very nice because we can put them together. We can take these intervals together, stack them together, and we don't add up any cohomology. We still have an half-open interval. This is kind of another example. It's not a manifold, but we can take such pieces and we can, it's like Lego pieces, put them together. So in this case, we get a closed loop. So we capture a 1-dimensional cohomology. So in this case, we can stack them together. We can actually build with such things. We can build any 1-dimensional simplicial complex. And here's another example of also not manifold-like, where we have a star. And so it's the open star in a star graph. And in this case, with that, we have the Betti vector is 0, 4. And you can explicitly compute this. I like this because this is what we teach in linear algebra, right? We have here a 6 times 6 matrix, 2, 4, 5, 6 times 6 matrix. The first block belonging to the 0-dimensional part is just invertible, and this part is far from invertible. It's one of the fun examples in linear algebra where you have just really kind of you're really fun to row reduce and really fun to compute the kernel. It's a 4-dimensional kernel, and so we have the Betti vector 0, 4. That's the Dirac matrix, which is the D plus D star. This I already mentioned also last time. It's kind of an open, if you have taken open cylinder, so you can also stack these open cylinders together. They have no cohomology, so you can put them together. And you can put an end to it, which is closed. This is a closed disk or an open disk, which captures just where you can put them together and you can build manifolds. Actually, this is a very nice example here, which is a torus where one open disk is taken away and one closed disk is taken away. So you can stack them together, right, to build any surface of any genus, orientable surface of any genus. And so I also already mentioned last time that it's not always working, right? When you take, for example, you take the projective plane, you take an open set away. So you capture you want to capture the volume form, but there is no volume form because it's not orientable. So you cannot. So when you take that away, you get the Moebius strip, and so the Moebius strip, it's a closed Moebius strip, which has the same cohomology, of course, like the circle, because it's homotopic, so it's 1, 1, 0, and the projective plane has 1, 0, 0. So you can stack them together with an open and a closed one to get a Klein bottle. So when you take this and this together, you get the Klein bottle. And here is an example I made also some computations in higher dimension. I take a 3 torus and take away, it's like this, I take away an open ball and a closed ball, and then I can use them to generate 3 manifolds. Just stack them together to produce 3 manifolds every time I get the Z 0, 3, 3, 0. And you can do that in any dimension. So that works. This is a situation which works. Here is a situation which I realized only last Monday, that it doesn't work. So if you take away, you take a 3 sphere, like our universe might be a 3 sphere, and you take away a solid 3 donut, right? A solid torus. This is also a 3 manifold with boundary, and then you can compute the cohomology. It doesn't add up, right? This 3 sphere has 1, 0, 0, 1, and this, when you compute that, you get 0, 0, 1, 1, and here you get 1, 1, 0, 0. So the Euler characteristic of course works, because these are real complements of each other in the 3 sphere. You take that, the complement, of course, they add up, because Euler characteristic is just counting. It's quite an interesting area of experimentation. I have to kind of understand this, of course, much more. And I close this now.